before we start, one thing really quick about me, so that you at least have some idea of who I am. I'm a physicist by education, so I have a master's in physics, but I'm doing computer science. Currently, I'm working in MBition, which is basically building a infotainment-based platform on embedded Linux. I've been using C++ one way or the other for more than 10 years now. So I'm pretty enthusiastic about programming language, and I try, especially with C++, as you may or may not know, is kind of a language with dark corners, and I enjoy exploring these dark corners. So, and also not completely relevant to this talk or anything. I'm also a dance sport teacher, so if you ever come to Berlin and want to learn to dance, you can hit me up. Okay, so let's talk about the problem that I'm going to solve. For this talk, what I'm focusing on is the basic idea of what async is, why we care, how we can tackle this in C++. So it will be more of an introduction, and what I'm actually most interested in is then in the end your questions, your feedback, your let's discuss how have you dealt with it, what are your thoughts on it. So it will be more a high level thing, but let's see, there will be some code. Okay, so the problem. If you look at modern hardware, you have components in your system, and actually quite a lot of components. And these components, they have different speeds at which they operate. For instance, you have the CPU, and you have like a clock cycle is in the order of nanoseconds, mostly, like even sub-nanoseconds, right? And then you have other things. In order to get something from the cache, like L1, for instance, you already have to spend like 1 to 5 nanoseconds, right? It's still nanoseconds, but it's a little bit slower. So while you fetching something from the cache, your CPU can do a few cycles, do something. Now, if you go to main memory, it gets even worse, right? So you have like a shift of a few orders of magnitude, where if you want to get something from main memory, the CPU can do like hundreds, thousands of cycles, right? And then it only gets worse, right? Hard disks even further away, so you have another order of magnitudes between this. So what will the CPU do while waiting for this data to arrive? And then things are getting even worse if you have like the network. You don't know when or if your data will arrive eventually at some point. So your CPU will be very bored if you wait on that. And of course, same goes with the weird source of asynchronicity, which is the user. You don't know when they're going to hit the button or when they will move the mouse or anything. So there's a lot of time that you can spend waiting for this, and maybe you don't want to. So the basic problem, or the challenge that we were trying to solve is, what do we do with the time when we're waiting? So if we're a classic single-threaded program without any async, usually what we have some instructions, like these little boxes here are kind of like, you can think of function calls or instructions, doesn't matter, like some work, right? And then you want to do something like read a file. So you would call a function, and then that function would read a file. That reading the file is still some more functions or some tasks, right? And then once you're done with reading the file, you get back to where you were, and then you can continue with the contents of the file, for instance, or something like this. And you have like between starting to read the file and ending to read the file, you're basically just waiting. So, or the execution is waiting for that operation to finish, which may or may not be bad. But if that operation is something that can be done in hardware on some other part of the system, in parallel, like reading from cache, reading from main memory, reading from the internet. While that is going on, your thread of execution actually could do other things instead of waiting. So instead of having this synchronization point with the thing that you called when we enter async, then what we do is still we call the operation like reading the file or reading from the network. But then instead of waiting, we just continue with our thread of execution. We just trigger and then we never look back. We go forward. And at the same time, when that operation finishes, we go somewhere else. So we continue after the asynchronous operation with something, right? So there's no waiting on the caller, and then there's no synchronization. And no synchronization is why we call it async. Okay, so let's look at a few, or let's look at actually one example. Like let's have a small web server, for instance. Yeah, so first we'll look at something very simple just to get the concept of what's going on, which is a web server is basically just a loop saying, okay, I wait for the next connection and I accept it. That is something that we have to wait for the user to actually do something with our server. Then I read the request. It's an IO, so I have to wait again. Then I read the file, maybe from my hard disks to order to send the response. Like this is like a static website that is just read from file. Okay, and then in the end, I have to send it back to over the network. And all of these things, so the code is very simple, right? So you can understand what's going on and you know, aha, these are the steps. But unfortunately, this web server would be very, very poor in performance because if one connection currently is going on, no other connection can happen because we're currently waiting somewhere else. So if we can make this async, then we could stagger these different connection requests. So let's look at what we can do with this. So in C++ specifically, we don't have many good primitives in the language itself. There are very good frameworks and libraries, but they're not like the tools that you have are a little bit limited. But one tool that you do have, and that is a very basic but very powerful tool if you walk with it a little bit, is continuations. So let's look at this. So a continuation, basically you have a call to some function that is asynchronous. That's the model, yeah. So you come from above, you trigger your asynchronous operation, and then that asynchronous operation goes somewhere. You don't know where. Might be on a background thread, might be in hardware, it might like different computing unit on different core, different network location, who knows, somewhere. We don't really care for our mental model. It becomes interesting later, but still. And then the only thing you know about this, that eventually at some point later, this is going to finish and this will come back. And it will come back and then you need to attach something to this arrow that came back. So this is kind of the mental model that I want you to have. Like you trigger an asynchronous operation, it goes somewhere, and then it comes back, and you're responsible for doing something to the when it comes back. Okay, how you can do that in code would be, for instance, let's say you have a synchronous thing, read request, which takes some arguments, doesn't really matter, and it would return a value like the request, which could be a struct or something, like some data that comes back, some response. If you want to turn that into this continuation model, what you would do is, in the simplest way, everything stays the same, return type becomes void, and now you pass an extra argument, which is the callback, which is some function. For instance, std function would be one of them, but there are different choices there. Could be also as simple as like a function pointer or something. And with this little thing, with this little transformation, you basically made your read request function, or any function really, you made it async. or at least you could potentially make it async. How would you use that? You would call it, and then usually you pass in a lambda expression. So, and how that would work is, instead of calling the next instruction when this function is done, it would call whatever you passed in as the lambda expression when it's done. So in this case, the return value that used to be a real return value now becomes the argument to the function that you pass in as the callback or the continuation. Okay. If you happen to have a function that is synchronous and you want to make it asynchronous, you can always do that. Yeah. The simplest way to do that would be just to define the async signature with your callback, and then you execute it somewhere else. This somewhere else might be, for instance, a background thread. Right here in this slide, I just created a background thread and then I detached it. And then what would happen is, if you call this read request function now, it would return immediately and not wait for anything. But at some later point in time, it would still call the callback. Of course, this is something that you shouldn't do. So I'm sorry for putting that on a slide. Because it has a lot of issues with the detaching of threads. But you can think of this just like any background thread is fine. You could also post it on an event loop or a thread pool or something like that, or any executor really. But that's a little bit out of scope for this particular talk. So now you have basically idea of how in code it would look like to have async method. Yeah, if you now want to have maybe a part of this web server that we looked at, you could do something like this. You say, okay, we have like process requests. Some request comes over the connection. The details don't really matter here. It's just slide code, but you get passed in a callback from the caller. And now you want to do some asynchronous code, and in the end also want to call this callback. So what you do is, okay, you have read request, for instance, you pass a lambda expression as the last argument, and then you do something with the request that comes back in the function argument of the lambda expression, and then you do another async call, like in this case read file, and then you do something again, and then you do write response, which is also an async thing. And then in the end, you maybe pass the callback that was initially passed to the overall thing. And what you can see here is, okay, this is now just 3 functions, and there is no error handling whatsoever. It's already starting, if you squint a little bit at it, like it's a little bit hard to see what's going on, because you have these nested callbacks. So this is something that I would encourage you to avoid doing if possible. And I will show you a different way to do that. But it could work, right? This is something that maybe someone who has JavaScript experience knows very, very well, which is kind of the callback hell. Still, it works. It's just a little bit inconvenient. So to summarize this little section here, with just standard C++, you do have some tools in your toolkit to make async work. They're not very powerful. Well, they're very, very powerful tools, but they're not very full featured tools. So we're just passing around like a function or function pointer or callable object. You can pretty much model in your mind how the asynchronicity in your system should work, which is great. It's actually really, really fast compared to other schemes and frameworks, because it just has the overhead of, okay, you have to save somewhere this callback, and that's it. That's usually just one copy of some callable function. And the other good thing about this is continuations, or these callbacks, they are elementary, which means that if you have a API in your system that is using them, you can build any other higher level asynchronous framework or methodology on top of that. So all of the other things that I'm going to talk about or list today, you can build on top of continuations. So it's really worth at least understanding the basics of how to work with that. Of course, one major downside is if you have like these nested callbacks or callbacks in general, it's getting a little bit hard to keep track of what's going on. So you have to be very careful in the design of your system so that you don't lose track of what things are where. Okay, let's move to a way that you can get a little bit more structure into your async code. One thing that you can do is you can have state machines. I'm sure some of you already know state machines, but it's just a name in this case. So let's see. Let's see if look at our process request again. So the thing that with the nested lambda expressions that you saw. Conceptually, what you have, okay, you want to call something like read request first, then it goes away to somewhere to complete, then comes back, and then you want to attach to the end of it, for instance, read file, and that goes back. This is another async call, goes somewhere and then comes back, and you want to write response, also async, and it's basically the same structure. And one important observation that you can make now is that the overall process request that contains all of these little async functions has the same structure as the small things. So process request itself will also be something that you can trigger. It goes somewhere, or it might go somewhere multiple times, but you don't really have to care. But it will come back and it will give you the same structure and code. And this is a very powerful property. This is a property that you probably use every day for synchronous code as well, right? So that's basically how functions work. You can call functions within functions, and you don't have to care about the overall global system uh, or the state of everything if you make sure that you don't have weird side effects or so you can reason about things locally if you have this structure, because then you can build on top of smaller operations like read from file or read a byte from file. You can build things like read one line in file, and you can build on top of that process HTTP request, and you can build on top of that start server. And from every point in your system, it just looks the same way, which is basically means that everything is composable. So this is good. Okay, now how we do that in code. Let's say we have this process request. Oh, I see it's a handle request, but okay, slideware. Bear with me. Okay, so let's say you have this handle request function. What we want to do is we want to collect all of the state that we need in order to do this request into a little struct. Then this is just one way of doing it, but basically we want to create that state somewhere that it's not cleaned up. For instance, on the heap, like with make shared in this case. And then we want to say, okay, this little struct has to handle, like we have to poke it to start the async operation. Why we're doing this is basically, otherwise, if you would call this function and it ends, everything, all the local variables would go out of scope, and then you might get memory leaks if you want to use them, for instance, in the continuation or later when the call comes back. So that's why we put them in this little struct. And yeah, let's do that now. So okay, first of all, we have to, so this is the little struct. We have to first of all collect all the state that we need during the computation. So in this case, for instance, it might be the connection that we have to save. And we always have to save the callback, right? The thing that we want to come back to in the end of the composed operation, and maybe other things. So that is really, it's kind of like local variables, but instead of putting them in the function scope, we put them in the struct. And then we have the starting thing. the starting thing is basically where our async operation starts. And the only thing that we're doing here is, okay, we call one async function or everything that might be synchronous before that function. Okay, in this case, it's just one async function. We use the local variables, or in this case, the member functions of this little struct, the member variables of this little struct. And then, and here's the a trick to make it a little bit easier for us. We make a copy of the shared pointer that we created and capture it inside of the lambda expression. And then on that lambda expression, we call whatever is next after the continuation. Okay, so and this what is next, we can just define right there. So as another little member function. Okay, and now again, we repeat the same pattern. So we get our request, in this case, as the result of the async operation. We do some synchronous work, like for instance, parsing the path. And then we do another asynchronous call. Okay, and then again, same pattern. So it's once you get used to this pattern, it's actually really simple to do it. And then, okay, so what is this on content? So we need to provide a handler for this. And here at this point, we're done with the overall combined async operation. So in the end, we call this self m callback the thing that we defined in the very beginning. And at that point, the overall combined async function is done and can call the continuation that you attach to it. Okay, so but you probably either you know it or you don't. But if you don't, you might wonder, what is this enabled shared from this, which is a very good question. When we create a shared pointer, basically what we do is we have a scope, the function scope, for instance, and then you do make shared. In that point, you create this little struct somewhere on the heap, and the shared pointer has a reference count, so it knows when no one's pointing at it anymore, and then we'll clean up everything. Okay, so after you created the shared pointer, you call the first async function, and you pass in as the last argument the continuation as the lambda expression, and you will capture the shared pointer by value, which means that the pointer count will go up, the reference count will go up. So now you have two things that point to the same shared pointer. Okay, since it's an async function, after triggering the operation, the initial function doesn't have to do anything anymore. So it will just go out of scope. At that point, we don't refer to it anymore. Everything that's local to that function scope is going to be cleaned up, and you only have the continuation. Then at that point, at some point, your operation finishes, like the network data is there, or the file has been read, and the callback is called. And in the callback, if we have another async function to continue, then we will do the same thing again. We create the closure, the lambda expression, then capture the shared pointer by value to have another reference point, and then the calling thing goes out of scope. And then at the very end, after the last piece in the chain has been done, there's no handover of this shared pointer anymore. Okay, so this will go out of scope, and then no one will refer to it. This count goes to 0. So at that point, we can just clean it up. And with this little pattern, you can basically, and of course, you have to be a little bit careful, but you can make sure that your data lifetimes are correctly handled, even in the face of async. You only have to remember everything that is used in the continuations of any of these things should move into the struct that you created for this little thing. And that's basically just what this, in this case, the state machine means. You can also do other things, but let's keep that for later or for questions maybe. Okay, so there are some trade-offs with state machines. State machines are still very fast because you basically have this one shared pointer that will keep your reference alive, and it's actually also just this one heap allocation that you will have for an asynchronous operation. Still, that might add up, so you might want to avoid that. One very good thing is you don't have nested callbacks if you're doing it carefully, and if you squint at the code, so let me go back real quick. You squint at this and you order it in the way that things are should happen chronologically in time, then you can see kind of what's going on with this request, right? You first have the read request, then you have the read file, then you have the write response. So you can lay out the code in a way that's a little bit more boilerplate than if you would do it synchronously, but it still kind of reflects the logic of the function that you have. And it's a local function, so sorry. So you would still see what this combined async operation is doing in the code. So almost linear. But of course, there's nothing stopping you from defining, for instance, these member functions of the state in out of order or in any order, really. So it might be a little bit misleading also if you don't take care that you are and make sure that you evolve the little struct as the code evolves. And the actual functionality will still be spread out a little bit. And it gets more complicated if you not have just one way through the async operation, but if there are forks, like, okay, at this point, if I get that back, then I will trigger something else, and if I get something else back, then I will go another way. So at that point, you probably want to make more use of the real state machine, in the sense of you define which states are accessible from where, and do maybe also have like a little supporting illustration how that works. Okay, anyways, so these are the things that you can do basically with any recent C++. The next thing, futures and promises, is something that you may or may not be able to do with current C++, at least not with the language alone. So first, let's see what it is. So if setFuture, for instance, is meant to be a return type, so you, instead of passing void and a continuation, or just the result in syncland, we return a future, which is kind of like a token for some time in the future, this thing will respond to a value. And that is the thing that you return. What can you do with that? You can call the function, get the future back, and then you can ask the future to say, give me your value now. And if you say, give me your value now, like with get, then the thread will block and wait until the value is there. So what you have is basically a tool to do a synchronization point for an asynchronous operation. Unfortunately, for STD future, so the future that comes with the C++ standard, at least right now, that's the only thing that you can do with it, really. And that's not very useful, because if you cannot, without waiting, do something, then you have no way to get the full efficiency out of the hardware, because you either are waiting too much because you called get too early, or you might not be able to start with the operation as soon as the result becomes available, and you will wait too little, so to speak. There are other future implementations. For instance, Boost has one, Folly has one, there's HPX. And what these implementations add over the standard is a .then. And that's kind of the most important thing that you want to have, because when you have such a future, you could just attach a continuation to it. So same thing again, You have like something like read request, which returns the future, and you say that f dot then, and then you put some code that should be executed immediately when this request finishes at some point in the future. You don't know. Okay, so this doesn't look much different from the continuations that we talked about in the very beginning. The main difference is that if you return a future from the lambda expression that's inside of the dot then that will become the return value of the overall expression. Okay, that sounds maybe weird, but the way it works is that you can chain these things. So you can say dot then read file and then dot then write response, and you can chain all of these operations. And what this does is it moves your code to the left. So it solves this callback hell problem because it kind of linearizes the calls that you're having, which is already something. So you can do another one dot then and so on and so forth. So you can compose asynchronous operations much more easily. So if the futures also have some trade-offs, right? So they're actually easy to compose asynchronous code, and the code flow will look really nice. And you can also handle errors, which is something that, for instance, with the state machines, you have to really think about how you're doing that. There are some algorithms like when all, when any. For instance, if you have multiple futures and you want to do something when one of them finishes, or you want to do something when all of them finish, and so on, you can write these kind of functions that generically express these kind of combinations with futures, which is great. It also has some downsides. So it's a little bit hard to maintain this because usually how you do this is you put lambda expressions in the argument to dot then. It can be any callable thing, but most of the time you put lambda expressions. And then you have like a chain of lambda expressions. It's very easy to fall in the trap of saying, oh, I have this tool, I'm going to use it, and everything will be one function again with 10, 20 dot then chains. And of course, that will be very hard to maintain because you don't see any more, similar with big functions in general, what's going on. One much bigger problem, at least in my experience, is that if you put the return type as the future or any future, you really are in async land. So all the functions that call this function should also return state future. And all the functions that call that function should also be returning state future. Otherwise, you will have a problem because you will be waiting. And that can result in you just wanting to make one little operation asynchronous for performance, and then having to go through your whole code base and refactor everything to return state future. So that's kind of a maintenance nightmare, if you will. So you have to be careful about that. And there is actually a non-negligible runtime overhead with these things. It depends, of course, on your domain and how performance critical your code is, in your opinion. You should always measure to see if that's a problem or not. Okay, so the last thing that I'm going to talk about is coroutines, because they're the cool new kid on the block with C++ Sentry. But the good thing is you already know kind of how it works by just what I told you today, because coroutines is a way for the compiler to build this little state machine for you. And it's actually much better than the state machine you would build from hand, because it can know the lifetime of things. So it will not, for instance, do this shared pointer thingy. It will do something much smarter in many cases, not in all cases. So how would that look like? You still have this asynchronous function. There's no continuation. And the only thing that you have is these co-await keywords that were added with C++20. And what this basically does, it tells the compiler, at this point, I want to suspend execution of this particular function or this coroutine until the result is there, and then fill in the request, fill in the result, and then continue with this and resume this coroutine. So basically, it will exactly happen the same thing as with the state machine one. Only the code is much cleaner, and of course also the compiler will be much more free to optimize things. So you have basically the best of all the worlds, because it's easy to read. It looks almost synchronous, but it will still benefit greatly from doing something else while waiting. So if you have access to C++20 in your compiler, in your environment, then why not use it? Only downside is, I glossed over it, there is this available type that you return. And in order to make a type avoidable, there is some things that you have to do. And if you don't spend a lot of time looking into it, then it might be a little bit complicated to get it running. So that's something that really should be in a library, and it is. There are libraries out there that will give you access to coroutines, and you should probably use them unless you're interested. And in that case, definitely look into how you could implement your own available types. It's a very interesting journey, but that's out of the scope for today as well. At least we can discuss it later if you want to. Okay, so of course there are some other patterns that I didn't mention or yet. I will mention them and then I will not talk about them again, to also handle asynchronicity in your code. So lazy promises and futures is one. Fiber is a very important implementation, comes from Boost. Reactive extension is also very interesting for instance, for user interfaces, when you have lots of different events that come in from different sources and you have to react on them. Channels is also an abstraction on asynchronicity, that was very popular with, or is still popular with Golang and Clojure, for instance. And it helps you really structure your code in a more simple way. So that's something that also exists. Continuation monad. .then already is a continuation monad, but if you're a little bit more into functional programming, can look up what that means. And probably there are much more. All of these have to in common that for C++, you really want to have a library that is doing the framework for you. And that has the downside that you have to choose one usually, or you have to pull in a lot of dependencies just to have this asynchronicity. So you have to be doing some investigation on what makes most sense in your particular problem domain. Okay, so conclusion. If you take anything with you, then for today, I would want you to take with you that callbacks are really the building block, the basic building block for async. You should really know, even if you use any of the other mechanisms, you should really know callbacks and how to utilize them for asynchronicity. Because in the worst case, there's something that you can put on an architectural boundary, which means, for instance, you have a library. Inside of the library, using the most fancy reactive extension something library to do your asynchronicity, but you don't want to force your clients to also use that. So you put just a callback on the interface, and then they can choose whatever library they want. Futures is one way to compose these asynchronous operations, which is something that also changed recently a little bit. So there are more proposals on the standard side also, to even not really extend future anymore, but to do something else, which is structured concurrency. But still, it's good thing if you have Boost, for instance, available to use that. Probably most people in 5 years will use coroutines for async. And I would expect that more and more libraries that are really good will come out of coroutines, because this is really the most easiest way for developers to do something without having a super in-depth knowledge and without having too many little nuanced things that they have to take care of in order to make async work correctly. And it's a nice journey to just venture out there and see what kind of patterns do exist. It really is a brain teaser. At least for me, it's always very interesting. And the main takeaway is async starts in your head. It's not a code level thing. You have to design your software to be able to even handle asynchronicity. So you need good design. You need to think about it. You shouldn't put this in ad hoc. I mean, you can, but then you will have a nightmare on maintaining that. So, and with that, thank you for your attention, and I'm looking forward to your questions.
First question from me, Oliver. What
Yes.
image is that?
Sorry, what?
What image is that?
Oh, okay. So this is an illustration of a black hole.
Yeah.
It's not a photo. I think there was a photo recently taken from a black hole, but it doesn't look like that exactly. But funnily enough, it is physically almost accurate, even though it is an illustration.
Including the jets.
You have the jets, you have the matter disk. Anyways.
Maybe one question, Oliver. Like, so you mentioned at the end of it, like about the design of such a asynchronous, right? Like that's the difficult part. So
Yep.
you know that in software systems, like usually it's difficult to do, like it is in your mind, but it's translated into the code and then the context is lost, especially for such kind of asynchronous design. How would you maintain that context, right? Like how would you document it? How would you make sure that the others get that context when somebody else is maintaining it?
Yeah, so it's a very good question. The I think there are two tools that you can utilize. The first tool is to create in your code as much abstractions as possible, in the sense of, if you, for instance, let me try to go back here. If you have something like this process request, yeah, this guy here. Okay, so if you have something like that, if you are able to make the interface of process request in your code look structurally the same as the API for read request and read file, and if you use the same convention of how to use async throughout your code, then you will get the benefit of not having to think about what is inside of the box, right? Instead of thinking about this, you can think about this.
Mm-hmm.
And if you manage to establish that the outside form of these things always look the same, then you will already have documented also things about, so for instance, if I see this kind of thing in code, I know process request is responsible for cleaning up its own mess. So any state that is not coming back through the continuation is something that I don't have to care about, which is good. On the other hand, if I write an async function, I have to care about it, so that anyone who's calling me doesn't have to care about it. So that's the one thing in order to make these kind of things. So use the same kind of Lego pieces on all the levels of your code base. And the other thing, if you have more, so these are these call it once, and then in the end you have one continuation. Of course, that's not always the case. Sometimes, as I said, you have forks. Sometimes you have different continuations based on what happens during the request, right? And in those cases, it makes sense, for instance, to draw these state machines so that you have like a little picture of what can possibly happen. And if that picture is, for instance, auto-generated, that is even better. So if I mean, you can do state machines, so you can have a formal description of the state machine and then use that formal use that formal description to both generate a diagram of the thing as well as the code that actually has the async operation. So that's another thing that you can do. Of course, the best thing that you can do is actually have like a clear design in mind and communicate that through the names of the code. Anything that is inside of the code is something that is the truth, so to speak, and everything that's next to the code will be additional maintenance.
True. Especially in large projects, right?
That's right.
Maybe another question is like, so you mentioned about like this kind of like all this asynchronous operations in different forms, right? Like, have you used any tools to do like, because that's something that I'm always missing. Like, how do you benchmark them? How do you measure? Have you actually made them useful? Like, compared to the synchronized operations, have you done any kind of benchmarking, like to compare your same operation in both these modes?
Yes, and that really depends on your problem that you're solving, right? So what does good performance mean? And if you can answer that question for your problem, then it is actually not that hard to measure it. So for instance, if you care about throughput, like messages per second, in talking about a web server, for instance, that's something that you actually can measure pretty easily, right? You can just start a server, I don't know, and send a message with an ID 1 to 1 billion something. Just spam it as quickly as you can, and then see how fast comes the response. And you have then you can measure your throughput. And or if you do latency, that's something that's a little bit more tricky to measure, especially on modern systems where you don't have real time. So, but still, I mean, as soon as you know what you want to measure, you probably can. And then it's more a question of measuring it correctly. And I agree with you that the tools are a little bit less mature than the tools that you have for profiling your regular applications. But you can still make use of them because, for instance, in code, what you could do is you can join at the end of your operations, right? So you start at for instance, if you want to benchmark process request for something, you can have a function around it, like your benchmark runner. You call it a bunch of times and it goes off to somewhere. And then at the end of the operation, when you actually want to do the measurement, you can just wait for all of these requests to come in back. And there are algorithms. So if you have, as I said, these callbacks are elementary. So you can build a generic wait for finish. So basically this .get, you can just build on top of that. And then you can wait until all of it's finished, and then you use the same tooling that you would use for sync.
Oliver, for as continuation, you can give a lambda. That's good, and it progresses the the work of the process further. But in case of exceptions, I think these frameworks that you had mentioned, I think they also take an exception continuation also, or an exception callback, perhaps.
Yes.
I was trying to look up Boost, but I didn't find, so I just.
Yeah, so there are two different ways you can do this, or well, there are more probably, but two main. The one thing that you can do is the return value becomes in the continuation becomes the argument to the lambda expression, right? So what you can do is just have another argument, which is something like an exception pointer. And at that point, you basically have something similar to an error code. You can just ask exception pointer, are you a null pointer? If yes, then then there was no exception during this asynchronous call, and you can continue with whatever you want to do. So it's a very common pattern to have in the lambda expression, like first argument, for instance, being always an exception pointer, and the second argument being the actual return value. And then you have like a little if statement. If there is an error, return early and do some error handling. And if not, then continue with the actual operation. That's one thing that you can do. And as you said, there's also for these monadic interfaces like .then, you usually have a .catch as well. So what you would do, you would compose your happy path. So when everything works well, you do .then, and then in the very end you do a .catch, similar to a try catch block. And then if any of the operations fail, it would skip over all the remaining .thens and immediately go to the catch. And you have the same thing with coroutines, for instance, as well. So you can actually use exceptions, like normal exceptions in coroutines. So if any of the async operations fail, then the coroutine would actually be woken up, so the resumed, but in the catch handler of the coroutine. So it would work the same way you would expect it to work in the synchronous way. And of course, different frameworks have different ways of doing this, but these are the two most common. So either an additional argument to the lambda expression, or an additional .catch argument, or even sometimes you also have like an overload that doesn't take just one callable for the continuation, but two callables, one for the actual continuation and one for the error handler.
So when you say the catch handler for the coroutine, you mean that entire block which has several coroutine invocations? I can place it in a try catch, and that's the same catch block which will be invoked, right?
Yes. So coroutines. Yeah. So basically, if you wrap this whole thing into a try catch, and then read request fails, you would end in the catch. If read file fails, you would end in the catch. Even if, and that's the great thing about coroutines, even if asynchronous thing fails with an exception, you would still end up in the catch. And there's some magic in this awaitable type to make that work. So under the hood, you would still have a indicator of it failed, similar to an additional argument to the callback.
That's good. Thanks. I had one more question on that last slide which you had. You mentioned to have callbacks on the boundaries of your library so that your users are not bound by something. So can you just restate what you said?
Sure. So the basic point is that if you have a callback, you can build a future, for instance, on top of that. Because the simplest way, you create a future and then you call the callback as the part of the .then, right? You can also build coroutines on top of callbacks. You can also build state machines on top of callbacks. You can build any of these abstractions on top of callbacks. So and also most of the libraries that are out there for async, they care about integrating with your code in particular. So most of the time there is some kind of helper that helps you. For instance, if you have like a C API, an async C API, you have a function pointer as the last argument, for instance. And they have a helper that will take that function. You will tell it, okay, the last argument is the callback, and then it will build whatever abstraction on top of these callbacks. So if you provide an API that has a signature with just the function arguments, and then the last argument being a callback for async, then I can do whatever framework I want to use. I can use that on top of your library, and of course that makes the whole, it makes it much easier for me, because I don't have to build weird glue code where I have to know the internals of the framework that you have used. Does that answer your question, or does it clarify?
Yes, yes, it does.
Okay.
Hey, hi, Dilip here. Thanks for the overall sync operations and future and promise related things. One question is regarding as we have our legacy C++ code base or Boost legacy codes, so we do not have this async or future and promise things. So is it possible for us to implement similar way of async with the help of multi-threading? And another question is like, is there any difference in a performance or speed with the using future and promise, or similar kind of implementation with the multi-threading?
So I can, of course, not say definitive things about performance, because that will depend completely on the overall setup. But, so first, the answer is yes. You can definitely. So if you have a synchronous function, then you can make it asynchronous by putting it, for instance, on a background thread. Or much more useful would be to put it on a thread pool, for instance, if you care about performance, that you can fine tune how many threads should there be used for async operations in your code base. So you could keep the sync stuff around, and you could reuse it to make it async. Definitely, and that's, for instance, a very common pattern in UI code, right? So you have some operation that maybe takes longer than 500 milliseconds, so the user would notice if you would do that on the event loop, and then you just put it on a background thread. And that's basically making it async. So definitely. As for the performance, that is something that really depends on the environment that you are in, because if you, for instance, if you not create a background thread when you call the function, you will have an overhead putting all the data onto that background thread, right? If you do create the thread at that point in time, you will have the overhead of creating the thread, which is dependent on your operating system. If you use .then, you will have a hidden mutex, because it will have to make sure that if you do call .then and the operation already started, that there is no race condition. So there is a performance impact on using .then. It might be small depending on your application. It might be big. It depends on so usually you want to use async for code that is IO bound. So meaning code that which speed is limited by the amount of IO operations that you can do. So looking into the network, reading stuff from the file system, reading stuff from main memory, these kind of things. If your code is limited by CPU, then async will not help you performance-wise.
Okay.
Because then it will create additional overhead. So you have to always balance out how much time is spent on IO versus how much CPU is spent on implementing these mechanisms to make your existing code async. And that's something that you can measure. So as a test, I mean, something like this, if you have a thread pool that you can just post any tasks on, it's very simple similar to this, to just make your code async and then check if it's faster or not.
Yes, thanks. I am currently using Threadful itself, like a boost thread group. So that way I'm currently achieving these things, but still in case of independent of IO operations, if you need to perform simultaneous operations, so in a legacy code, there is no such a future promise, those kind of things. So thought of asking this question in such a way we can use it. I got your point overall. Thank you so much.
Okay.
Dilip, you can propose an upgrade of your tool set.
Yes, I'm in the process of that, but for the security point of view, they have the diagnostic based software that they are not willing to do it immediately, but in near future, obviously, that will be done.
Yeah, the more we modernize our code, the better
Yes.
it is for ourselves.
Right. Yeah, thank you so much.
Yeah, I want to say that if you are doing asynchronous code, at least get a library that implements something like a future. I built, there was a web server called Rogon in C++, which I was using, and it was based on callbacks, and it was hell because you have callbacks nested inside of callbacks, nested inside of callbacks, and at like after 3 callbacks, you start having seg faults because you don't remember which things you are copied into which lambdas and which things you have moved in and they no longer exist, and like it was just making my head burst. So if you can just please use something like a future, because that will save you a lot of code, and because of the indentation you can't even see the entire code in like one proper file even if you have a big monitor. So
Yeah, definitely. I totally agree. So yeah, I would even go a little bit further than that. It's not as much about the library itself. It's about having a strategy how to deal with this. So not every function should reinvent the way in your code base async is handled. So for instance, in the code base that I'm currently working on, we're not using futures actually. We're using callbacks, but we kind of factored out or extracted common functionality that we use all the time. Like for instance, this composition of having multiple things after one another. We had have a little way to get that right. And if you have that, you don't necessarily need like a library. It depends on, again, on your ecosystem, how easy it is to introduce your library, right? If you can choose, sure, use one of the sophisticated libraries, definitely. So whatever makes you able to think about the problem that you're trying to solve instead of the minute details of did I correctly plug in the right things in the right places? Definitely. Okay, are there any more questions?
A question on the chaining of the futures. When we chain the futures, and you're there, Oliver?
Yes, I'm here. Sorry.
Okay. Yeah, I just switched the view. So when we chain them, you get the absolute last future that you have. Okay. And you don't get all these intermediate futures because they are consumed by the calls. And then in such a case, when we have to come to cancellation.
Yeah, I see where you're going with this. Okay.
I have some experience, so we have had to hold on to each of these features on the way. I don't know if you have an answer to that or.
Yeah, I mean, okay, so I have multiple answers. One thing, coming back to this mental model, and I just want to highlight how really important this is, right? So if you have a good mental model also for cancellation, then it is not that bad. So one thing, for instance, that you ask, I think, even, is I can put a dot catch here, right? And then it will make sure that this is called when when anything fails. Cancellation is basically a special case of an exception that's happening, kind of, right? So you could handle it in a similar way. If you have such a chain of .thens, actually what is happening is you don't get rid of the future, so you don't actually get only the future, only this part in the end, or sorry, only this part in the end. But you get actually a future that is the combined future of all of these things. So you would still have all of them around. And if you put in as part of your framework a cancellation, then you would still be able within that framework to make sure that you cancel at the appropriate time. Two examples of this. One is Boost ASIO, for instance. Boost ASIO is also using callbacks, and what you would get is an error code as one of the arguments to the lambda. So basically, instead of just having the result, you would get a boost error code, and then the boost error code you could ask, were you canceled, right? So that means that the operation that actually didn't happen, but somewhere along the line this thing was canceled, and then you can handle the cancellation. This is one thing. The other thing, which is currently being proposed for the standard in the executor technical specification, I think I have to look up the link if you're interested, is to do a little bit more structured concurrency. In that case, cancellation would be part of algorithms. So if you have something like when all or when any is a good thing. So when any, how that works is you have multiple async operations, and as soon as the first one finishes, the whole operation finishes. And in order to not have any dangling async operations, all the other operations that are still pending will be canceled. In that case, cancellation would be part of the algorithm. So you have to implement it in that algorithm, and you have to implement it at the leaf node. So any operation that you write yourself that you know is cancelable. So for instance, if you have something where you do a little bit of work, and then you look if you're canceled, and then do a little bit more of work, and then you look if you're canceled, like that, you can make it cancelable. And if you use that same strategy, then your algorithms will work, and then you can implement something like a fetch for something from the internet with timeout easily, because you can just say when any, either the fetch finishes or the timeout finishes, and then the respective other thing is being canceled. But it comes down to having the mental model again, unfortunately or fortunately. So the depends a little bit on the library that you're using, if that mental model is imbued in that library or not.
I can think of a good way, because the library has the reference to the future it is creating. It can just propagate the cancellation up if the future is not yet completed. Like,
Yeah. So yeah, sure. I mean, you have two options, right? So one is
yeah.
Your operation has already started. So for instance, it is already starting with read request, but it hasn't started yet with this. Then of course, if that is canceled, you maybe not be able to cancel that operation anymore because that is already on the way, but you can cancel everything that happens after.
Yeah.
That's what you mean, right?
Yeah, I just meant that because we are chaining .thens, we have a reference to the future. The library has a reference to the future. So that is this chaining .then on. So if we cancel the second .then, it knows that it needs to cancel the first .then as well, because the first depends on the second one.
Yeah. So basically,
So,
how these features are implemented usually are you have like a linked list of continuation. So you can usually go back